So we're beginning section 5.1. This is chapter 5, and we're going to talk about exponential functions. So this is a whole new class of functions to work with, and a whole different type of modeling that we're going to be doing. A lot of people find this unit to be a little bit more difficult than what we did previously. So I'm not saying that to scare you, but just to prepare you that you might need to put in a bit more time with this material. So let's start with talking about the algebraic definition for an exponential function. An exponential function is a function of the form f of x equals a times b raised to the x. And we need to talk about all the conditions related to each of these factors in the expression and as well as the exponent. So the first thing, let's talk about the base. So what is the base? It is the B letter here. Now we have an unfortunate overlap with using the letter B for a intercept in the previous unit, and now we're using the letter B to represent the base of the exponential function. You just have to accept that that's the way it's going to be, and try not to get confused. Okay. So what are the conditions related to the base? It has to be positive, and not only does it have to be positive, it can't be equal to 1. And the reasons for this are the following: if we didn't require that it be positive, then we could potentially have a negative base. And if you have a negative base, then you're going to be getting into complex numbers, aka imaginary numbers. And that's beyond the realm and the scope of this course. So that's why we make that restriction. The second restriction about b not being equal to 1 is simply because if we let b equal 1, then we would not have an exponential function. We would just have 1 raised to a power, and 1 raised to any value is still 1. So this would not actually show any interesting exponential behavior. So that's why we make these two restrictions. Nextly, the independent variable x is in the exponent, which hence the name of the function class. This is also called the power, less frequently the power, but this is the exponent. It's raised. Okay. Also, we have to deal with order of operation. That becomes a significant hurdle to get over in this unit. So just make sure you understand that when you are working with this function, that the b to the x is the only thing that gets raised to the x is the base. This a value is multiplied after that. Okay. And let's talk about this a value. Down here, we've got a bullet that deals with that. The a value is essentially, it's the initial value of the function. So it is the actual y-intercept for the function. So that's, again, confusing given what we did in the last unit, but this is a new unit, new day, so new letter, new meanings for the letters, I guess. But anyway, if you let x be 0, which is what's happening right here, we're basically saying a times b to the 0 is equal to a times 1, which is equal to a. So f of 0 is equal to a. This little f sub 0 is just a particular notation sometimes people use. So that's the y-intercept. So this is saying, this is called the initial value. So this is the value of the function when the input is 0. So whatever it looks like, it's going to start right there. And then we'll see what happens after that. Okay, so we certainly need to talk about what it looks like, and we'll get to that in just a moment. But let's talk a little bit more about this base. I know we just defined the b value, and I called it the base, but there's another very important name for this, and that's the following, which is This slide is particularly talking about the growth factor, but I kind of, in a general fashion, you can just think of b as the factor. And notice here I've got this restriction to if b is greater than 1. Well, let me explain what this is talking about. If b is greater than 1, we have a growth factor. But if b is less than 1 but greater than 0, then b is a decay factor. But in either case, it's the factor, okay? So we'll get into this in 5.2, so you won't see any more about this at the moment. We're going to be specifically focusing on exponential growth functions in Unit 5.1, okay? So as this says, b is restricted to be larger than 1 in terms of if we're talking about growth. When x increases by 1 unit, f of x increases by a factor of b. So factor, this word, you really need to kind of understand what we mean when we say factor. When I say factor, you need to think multiplication. Okay. So if I go over 1 unit, then wherever I was here, I will go up by multiplying this amount by b. So whatever this is, it's going to get multiplied by b. So if this is a, then this is going to be a times b. That's hard to read, isn't it? But it's not a plus b, it's a times b, okay? So that's an important thing to remember, is multiplication, okay? I want to go ahead, I know that I have an example here, but I'm impatient. I want to find, you know what, forget this for the moment, I'm sorry. Let's go to the whiteboard. I want to draw this dang thing. I want to show you what this looks like. So I want to draw a picture of an exponential growth function. And I'm going to pick one out. I'm going to do the function y equals 2 to the x. So in this example, my initial value is 1 and b is 2, right? So I don't, it's not correct to say that you don't have an initial value. You have an initial value. It's just that I'm not writing it here because it's sort of an understood 1, but it's sort of hiding there. So at times 0, let's actually make a little chart here. I'm sorry, that was supposed to be an x. At times 0, we are at 2 to the 0, which is 1. And let's go over 1 unit. And as promised, if I go over 1 unit, I need to multiply where I was by the factor of 2. So that takes me to 2 in this case. Let's go over 1 more unit to 2. And try not to run out of room here. So if I put in x2, I get 2 squared, which is 4. So that's 3, 4. So that's up here. Okay. Now I started at I started at 0, but I could put in negative values for this since this doesn't necessarily represent time or anything. Notice also that this value 2, when I went 1 unit over, I multiplied 2 by the factor 2, and that takes me to 4. So that's I just want to keep stressing that factor idea, that growth factor. So what you should see here is something like that, and this is going to keep on happening. If I put in 3, I would get 2 to the 3rd power, which is 8, right? And as we move to the left, what you will see is a function that looks like that. So just some general behavior here. This is negative infinity and this is positive infinity. So as x goes to positive infinity, f of x also goes to a positive infinity. As x goes to negative infinity, in other words, as we move to the left, what is f of x doing? It's not going to negative infinity. F of x is actually approaching 0. So we have what this means is we have a horizontal asymptote. And that horizontal asymptote is actually, in this case, the y-axis. Okay. So we can say some things about domains and ranges here. The domain of this function is all real numbers. There is no restriction on what I can put in. But the range is not all real numbers. The range, as you can see kind of indicated in this picture, is 0 to infinity. And this is non-inclusive of 0, so it doesn't actually get to 0. All right, what else can we say about this? There's a lot I could say about this actually, but let's see here. Well, what about concavity? This is certainly an increasing function, and it is concave up. So this is increasing and concave up. So that means it's at an increasing rate. So this is not a linear function. So that's kind of the high points of this function, some of the things that we've talked about in the past, like concavity and increasing and all that. And now that we've gotten some of those things out of the way, let's go back to our slides and we can look at an example. So here we go. This is a financial example, and you're going to notice that you will see a lot of financial examples in terms of exponential functions. And that's because exponential growth and decay oftentimes is the appropriate model to use. So we've got an investment account that's given by this following function, 500 times 1.04 to the t, where t is the elapsed time. Most if not all of our exponential functions are going to be elapsed time. So we're resetting the clock. Okay. In years after January 1st, 2018. Okay. So I like, before I even get into these specific questions, I always like to take a moment to look at my function and identify the parts. So for this one, 500 is my A value, my initial value. 1B is 1.04. That's my growth factor. Okay. And I guess that's it. Now we can look at the questions. The easiest one is this first question. What was the account balance on January 1st, 2018? That's when we started, right? And that's just A of 0. Which you could actually do that without any calculators. You can just do this in your head. If you put in 0 right here for t, then that 1.04 to the 0 is 1, and so we have 500 times 1, and so that's just 500. So that's my initial value, which we knew that already. All right, that's the end of my time on this video, so we will answer the following parts in the next video.